Right, hello. So today or tonight, not night yet, but this evening, we're doing something a little different. So normally I'm programming with Unity and C Sharp, but this evening I have started. I spent already a few days on this, and so this is like my first steps with Vulkan and C++. And yeah, so I'm just following the tutorial basically. It's not gonna be anything crazy. But yeah, so basically, so far, well, I've set up everything. English. Basically, we are past like setting up the project and the base code and the instance and the validation layers. Getting the physical devices and queue families and creating the logical device. I believe I finished this. I am not sure about that. I forgot to put the camera on. Right. So, specifying the queues to be created. So I believe we are doing this already. Creating the logical device. Let's see. We do have create logical device here. And yeah. Just check the destroy also. Not the cleanup. Yes, so we do have everything. And we can use the vk get device queue function to retrieve queue handles for each queue family. The parameters are the logical device, queue family, queue index, and a pointer to the variable to store the queue handle in. Because we're only creating a single queue from this family, we'll simply use index 0. Right. So, let's see this again. Are we actually, yeah. Here we get a handle over queue for graphics. This is like a common queue. I have no idea how to use it yet, but apparently this is what we'll use to send draw commands, I suppose. And we are storing this inside of this this private variable here that's part of our hello triangle app. And surely I should be doing the same for the prison queue, but at the same time, there's no point in doing so because I know they have the same index, so they are the same queue actually. If I run this. So, of course, right now we only have a white window. Yes, you can see the graphics queue and the present queue are the same. And we only have one. We only have one. So there is really no point in getting the present queue, although I think I'm still gonna do it since I created the variable for. I really need to learn what is the hey, you just woke up. Like, well, that's right in time. I just started, and we're doing something a bit different tonight. Well, this evening, which is no game engine this time. Going with raw C++ and Vulkan. Vulkan, if you don't know, is something like OpenGL. It's a way to talk with the GPU, basically. So yeah, we're trying to learn this, and we do this, then I can do this. Yeah, not ideal, but let's store our prison queue in here, and forget to use the right family. I just switched to English. Okay, yeah, sorry. Alright, so I want to warn you that it might be a bit boring because basically what I'm gonna do is just follow this tutorial here. But normally I've passed most of the boring stuff, hopefully, because like basically all of this took me several days to get through. Probably yeah, 2 days, I think. Yeah, probably like 2 days, but well, 2 days. I'm exaggerating. Like I did it in different days, but probably spent like 1 or 2 hours on each thing. Right, the window surface. I think I actually started this too. Yeah, so hopefully after a while we're gonna be able to finally draw something. Yeah, I mean, it would be great that we start displaying something on the screen because I'm getting tired of all this boilerplate code and like we still have nothing to draw. Well, let's see. Yeah, so I have started actually this part also. Or did I? Maybe I started reading about it. Okay, so we created the surface here. And we call the create surface. Okay, so I might have done this one as well. Do have a VK destroy surface KHR, yes. And we do have the create surface in here as well. We did do this, yes. Yes, because this is where you actually separate the queues, I guess. And yeah, this is where you actually turn this into a for each. Okay. Okay, so the only thing I didn't do was this, and I just did it. Alright, so swap chain. Vulkan does not have the concept of a default prime buffer. Hence, it requires an infrastructure that will own the buffers, we will render to before we visualize them on the screen. Okay. This infrastructure is known as the swap chain. It must be created explicitly in Vulkan. The swap chain is essentially a queue of images that are waiting to be presented to the screen. Our application will acquire such an image to draw to it. Yes, okay. And then return it to the queue. Okay. So exactly the queue works, and the conditions for presenting an image from the queue depend on how the swap chain is set up. But the general purpose of the swap chain is to synchronize the presentation of images with the refresh rate of the screen. Right. Right, didn't think about this. You have to synchronize with the refresh rate of the screen. Okay. Interesting. Checking for swap chain support. Not all graphics cards are capable of presenting images directly to a screen for various reasons. For example, because they are designed for servers and don't have any display outputs. Secondly, since image presentation is heavily tied into the Windows system and the surfaces associated with Windows, it is not actually part of the Vulkan core. You have to enable the VKKHR swap chain device extension after querying for its support. Alright, so it does support, or at least they have some kind of handling of this, but you have to enable it via extension. For that purpose, we will first extend the isDeviceSuitable function to check if this extension is supported. We've previously seen how to list the extensions that are supported by a VK physical device, so doing that should be fairly straightforward. Note that the Vulkan header file provides a nice macro. VKKHR swap chain extension name that is defined as VKKHR swap chain. Okay. The advantage of using this macro is that the compiler will catch misspellings. Just declare a list of required device extensions, similar to the list of validation layers to enable. So here we have a list of validation layers. So I'll create another vector of constant char pointer. I wonder a little like why this is a constant char pointer or and not a string. And then we can use the macro. Here's with vk chain function name. Okay. I don't even know what a macro is, to be honest. To me, like, this is just like a special variable. Well, it's just a variable, I guess. But suppose in this case it's gonna replace it just at compile time. Is a macro just a define, actually? You define something to be a value, and therefore it's the constant that the compiler knows it can just replace it with the value. Here. That's semicolon somewhere. Okay, so next, create a new function, check device extension support, that is called from is device suitable as an additional check. Supported, okay. And return, and this is the is complete and extension supported, okay. Alright, so we have this function here that's supposed to pick the which GPU we're gonna use, and we don't have a is device suitable, we have a rate device suitability. Basically, this one is gonna return 0 as the device is not suitable. So let's call this our device extensions supported, and there's a device inside. So write this here. Our device extensions support, and we want a BK as a physical device, yeah. Device. Of course, we want to return Boolean. That's just returning true for now. Is this correct? Yes. This is something that we require. Okay, and then modify the body of the function to enumerate the extensions and check if all the required extensions are amongst them. All right. Count. Okay, enumerate device extension properties. Here we pass the device, we pass what is it not giving rest here? It's not all of it, right? It refuses to tell me what's after. Oh, wait. Okay, enumerates device extension properties. Device Yeah, so it auto completed with some weird stuff. So we pass a layer name here, but we don't pass it. Is that the same thing that we were doing for the validation layers? No, we're doing instance layers then. Instance layer properties. Okay. So then the property con that we want to write into, and here we pass null because we need to know how many we're gonna get, and of course that's the address here. And then we can make a vector with the decay extension properties. Is that it? Real extensions. We initialize it with this is a really weird way to you actually have to call this twice. The first time you're just getting the count, and then and then only you get all the available extensions. Is it like this? I think no. Because this one is returning the pointer to it. I don't understand everything that I'm doing, but okay, let's do this string. We create a set of string and word extensions. What is this? That's where some of the signatures of these things are really unreadable. Which one are we using here? Is it first last? It's an iterator. Wait, no. How did I name this? This is device extensions. Is it not? Okay. Begin. Man, how the fuck are you supposed to read this shit? Like, okay, so the return type is actually only shit. The return type is only this part before my cursor. So it returns a const std vector of constant char iterator. Okay. I've rarely seen such unreadable code. Like the other example is just TypeScript, but when you get crazy with it. Although why is begin like first why are we passing two iterators in here, and why is there an iterator for begin and an iterator for end? And, it doesn't really make sense to me. You know what? I'm sure ChatGPT knows the answer to this. It's not gonna take me forever to ask it. The std set container is used to store unique elements in a sorted order. It's sorted. Initializing std sets with two iterators is a common and powerful technique that allows you to create a set from a range of elements. Well, at least it seems like it's understanding what I'm asking, which is great. This approach leverages the iterator range pattern, which is widely used in the standard template library for flexibility and efficiency. Understanding iterator initialization. Here is the syntax for initializing the set with two iterators. Yeah. Type is the type of the element in the set. Iterator refers to the type of iterator. Yes, I mean, it's explaining the signature, I guess. Okay. What is an iterator though? Like, I mean, is an iterator just primary reason to use two iterators is to specify a range of elements to initialize the set. It allows you to copy elements from any portion of a sequence, such as a subarray or a sublist. Yes, so that's it. You can create a set from any part of a container, not just from the beginning to the end. This is useful when you only need a subset of elements. Okay. Is this just returning an index? Then why not use... I don't understand why this is an iterator and it's not just like an index number. Hey Saif, welcome back. But man, I'm telling you, you better chill. Using iterators avoids the need for an intermediate container when converting elements from one container to a set. It directly constructs the set from the specified range. Okay, but like, what would you have to do if you didn't do this? Like, you have to copy everything by hand? Last exam before vacation, yeah, it's good, so enjoy it. This approach aligns with the principles of generic programming. Functions and algorithms can work with different container types by simply using iterators. I still don't understand like what this changes though. Doing a template here. fuck is going on here? You get 98 on average without studying? Yeah, that's good. What class are you in? Well, I'm telling you, because I've been like this as well. You know, I've gone through like school without doing much. You know, and I could always get like I could get enough to pass. You know, and I didn't have to work. But later in life, things will get harder, and you won't be able to get by without doing anything. Like for example, making a game or like learning this C++ stuff. Like no matter how smart you are, you will have to work hard if you want to be able to do this kind of stuff. So what I'm telling you is don't get used to it, you know. Because when you get used to it, once you have to work hard, well, it's difficult because you're not used to working hard, you know. Mm. Alright, I mean, sure. Sure, it's nice, but it's not really telling me why we are using iterators here. I guess I should not get hung up on this too much. It probably doesn't matter that much. I guess for now, what matters is this points to the beginning, this points to the end, and you can use it to create a set of all elements in between. Why use an iterator and not an index? I am not sure. But I'm sure there's a reason for it. Now, little for each extension in device. Yes. So, no, available. And don't we want to forage on required extensions? Oh, okay. So you're doing it like this. I wonder why though. Name. Why do it like this though? Because like we could just for each required extensions and check whether. Well, I guess then you would have to do a filter, right? Which would be more complicated, I suppose. Okay, I guess. And so we return whether our required extensions is now empty. Yeah, sure, planting trees sounds easier, but you might change your mind, you know. Anyways, I'm telling you because you know it's been my experience, but at the end of the day, I know you will not be able to understand it without having the experience yourself. Yeah, it's physical. It's physically difficult, which is a different kind of hard work, actually. Like in check validation layer support. So how are we doing this already? Check validation layer support. Mm, not the right code I'm looking at. Yeah, so here we do a for each on the validation layers that we want. Then, yeah, we do a string comparison between a layer name and this layer name. Oh yeah, yes, nested loop. Yeah, so that's the thing that I was thinking. We have to do a filter. Then it means like we have to have a nested loop that is going to check whether um, any of the layers are actually the one that we are looking for, which is. I mean, this approach here is, I think, much more elegant, and it's um, probably a lot faster as well. I mean, it doesn't matter, but I mean, it's a lot easier to reason about this than it is about this whole thing here. Alright, anyways, doesn't matter. Let's get going. So, check our extension, device extensions. Okay, so we are this function ready. I run the code and verify that your graphics card is indeed capable of creating a swap chain. It should be noted that the viability of a presentation queue, as we checked in the previous chapter, implies that the swap chain extension must be supported. However, it's still good to be explicit about things, and the extension does have to be explicitly enabled. I mean, we haven't done that, right? We've only checked the support so far. And yeah, I mean, seems like we had no problem, so it should be. Right, okay, now we are going to enable it explicitly. Using a swap chain requires enabling the VKKHR swap chain extension first. Enabling the extension just requires a small change to the logical device creation structure. That's good news. So logical device creation here. We have our device creating for here, so this is the one we are changing. Enabled extension count. Do we have this? I don't think so. It's the logical device, right? The logical device creation structure. So the logical device creation. Would I live in your country? I think I would burn. Uh, why the fuck do I not have extension count here? But it is present on here, right? Device info. Enable extension can, but we didn't do this in the previous code, so why are they saying it to replace it? Or they're talking about the physical device? I don't think so. Nah. No way. There's no way because we are not creating the physical device. The other thing that we're creating is the VK instance. Yeah. Info. Yeah, so I'm a bit worried that they are. Yeah, but same thing. Like I'm not going to. Wait a minute. Yeah, but no, we already have this, so it wouldn't be replacing by 0 then. It wouldn't be replacing the 0, so I don't think that's it. For me, it's here. So device create info. Enable extension names, and this we pass the device extensions. Data. This is a pointer to a pointer, right? Like this CP thing here is means pointer to a pointer. I think. Alright, so querying details of swap train support. Just checking if a swap train is available is not sufficient because it may not actually be compatible with a Windows surface. Creating a swap train also involves a lot more settings than instance and device creation. Creating a swap train also involves a lot more settings than instance and device creation. Well, that's fucking great, because I really thought like we didn't have enough boilerplate code yet. So we need to query for some more details before we are able to proceed. There are basically three kinds of properties we need to check. Basic surface capabilities. Min-max number of images in swap chain. Min-max width and height of images. Okay. Surface formats, pixel format and color space. Available presentation modes. Okay. That is interesting though. We are really in the low level stuff here. Like literally you have to take care of everything. Yeah. Similar to find Q families, we'll use a struct to pass these details around once they've been queried. The three aforementioned types of properties come in the form of the following struct and list of structs. Okay. So, the Q families, we did this for the swap chain support details. Why is this please stay here? So we have a struct that holds details about the surface capabilities. And then we have a list of surface formats. Yeah, I already forgot why there's KH everywhere. Formats. And then a list of presentation modes. I'm pretty sure they explained this KHR stuff before, but I forgot. So I'm gonna ask ChatGPT again. Alright, it's Kronos. The Kronos group, the people who are developing Vulkan and developed OpenGL. extensions in Vulkan that have the KHR suffix are standardized extensions that have been ratified by the Chrome School. Right. So this okay. So KHR is basically the standard extensions. Okay. Right. So now we want to query for this port. Okay. Where am I gonna put this? Put it here. We'll return a swap chain support details. And I'll call this query swap chain support details, I guess. And we take in the physical device. Oh, I'm sorry, but I think it's not today that we're gonna draw stuff on the screen. Holy shit. Huh? Alright, so we create a new product with our details and return it. This section covers how to query the structs that include this information. The meaning of these structs and exactly which data they contain is discussed in the next section. Let's start with the basic surface capabilities. These properties are simple to query and are returned into a single surface capabilities struct. Oh, right. Oh, because we're gonna write it directly. Okay. Get physical device surface capabilities. That's it. And so we pass the device, and then what? Surface, and where we want to write so details that these capabilities. Okay. This function takes the specified VK physical device and VK surface KHR Windows surface into account when determining the supported capabilities. All of the support querying functions have these two as first parameters because they are the core components of the swap chain. Okay. All right, I'm gonna get some water before we continue. All right. Because I needed to drink. Are you working right now? Um, Alright, so we did this, and now we go to this. The next step is about querying the supported surface formats. About querying the supported surface formats, yes. Because this is a list of structs, it follows the familiar ritual of two function calls. Great. So formats, format counts, and then we do what vk get get surface format vk surf no vk can't share as properties, no. I hope you like the piano. I need something chill and so I can focus on this stuff here. And understand something to it. Okay, I will read it. Get physical device surface formats. Device surface, and so it's still linked. I would have thought the formats are just for the surface though. Surface format count, so here we pass the format count, and then is the list, so we pass null pointer, and then we want a vector to all the formats. A so vk type here vk surface format here, and I typed it before. Vk surface format sure formats of counts, and then we do the same call again. Surface format count and and formats that data. Oh wait, but I don't need to do this actually. I'm not supposed to do this. What I need to do is put it inside of my struct here. Don't need this. Let's keep this together. Glad you enjoy it then. Doing 32T, and so now what are we going to do? We got the surface capabilities, we got the surface formats, and then what was the last thing? Presentation modes? Yeah. Present. We can get physical device present mode. Nope. Let's VK get device group surface present mode schedule. We can get physical device surface present. What did I type before? It was the same thing, no? Oh wait, they are writing this completely differently here. Oh yeah, because we need to resize it first. So if format count not 0, but after, not here. First we count, then we get the actual list. But first we need to resize our enum vector. Resize formats. And present mode count. And pointer. So suppose we're gonna do the same here. But I actually prefer to do this. It doesn't change anything probably, but I think it's just a better practice. When you expect something to be positive, or to not be 0, but you also don't expect it to be negative. Right, and so we resize the present mode list to the size that we got. Then we call this again. Surface as the device surface and there. Is it passing? I was wondering if it was passing a null pointer on the second call, but no. And here we pass our list. Here's the present modes, that data. Right, so with this we should have all the info. Sure that the vector is resized to all the available formats, and finally querying the supported presentation modes was exactly the same. all of the details are in the struct now, so let's extend is device suitable. Once more, to utilize this function to verify the swap train support is adequate. Swap train support is sufficient for this tutorial if there is at least one supported image format and one supported presentation mode given the window surface we have. All right. So in here, we are now also going to return 0 if the device is not suitable. So let's do, well, not if the device. All this is swap chain supported. And so first we need to query also we created a struct for to all this, but we didn't. Wait, where is the signature of this thing? Oh, yeah, created in the function. Okay. But maybe you want to hold on to this info, no? No? Okay. It's not. Okay, so I guess I'm gonna split this. So the first thing is whether the GPU is supporting the required Q families that we need. And this is given by Q indices that is complete. Then we have our device extensions supported, which is our device extension supported. So I will misspell it. What? Let's say the subtrain support here will initialize to false, and here we pass supports required Q families. The hell? Who's this? Oh, it's because it's named the same. Yeah, that's unfortunate. All these extensions supported. And finally, if the swap train is not supported, then we also we also get out of this with a score of 0. If our extensions are spotted, then we check for the support, which means creating our swap chain support details struct. Querying it with device, and the setting is swap chain supported to. So we said if there is at least one format, a size or length. Is superior to 0, then we need at least one, and we need one format, and well, one present mode. That's it. And this is the same thing, right? If I do size superior to 0 is same thing as saying not empty. Fine, I write it this way. I want to spend 4 hours to later find out that this wasn't the same thing. I'll just follow it. Okay, so yep, okay. It's important that we only try to query for swap chain support after verifying that the extension is available. The last line of the function changes to I could split this into multiple returns. Yeah, actually, why not do this? Yeah, no, never mind. No point in doing this. If the swap chain adequate conditions were met, then the support is definitely sufficient, but there may still be many different modes of varying optimality. We'll now write a couple of functions to find the right settings for the best possible swap chain. Of course, there are 3 types of settings to determine: surface format, color depth, presentation mode, conditions for swapping images to the screen, swap extent, resolution of images in swap chain. Okay. For each of these settings, we'll have an ideal value in mind that we'll go with, if it's available, and otherwise we'll create some logic to find the next best thing. I guess. Oh wow, this is fucking long as hell. Oh shit. Yeah, we're definitely not drawing anything to the screen today. Alright. Alright, well, let's get to it then. Surface format, the function for this setting starts out like this. We'll later pass the format's member of the swap chain support details struct as arguments. I did not understand anything of this sentence. The function for this setting starts out like this. Later, okay. I don't read the punctuation, so I don't understand anything. We'll later pass the format's member of the subchain support details struct as arguments. Okay, so why? I guess we'll just pick in place inside of rate device suitability. Okay, surface format K R use swap surface format. I should not have looked at the length of this because now I'm getting discouraged. Oh, it's gonna take forever still to do this before we can draw anything, and it's so long to get anything on the screen. Okay, so we pass in a list of formats. We pass them in as a reference. I think that's what this means. Because we are passing the address of this variable, if that makes sense. I'm not sure why they use const in here. See if the GPT explains. Explain the use of the const keyword. Signature. Huh? Is it smoking crack or what? Was it used in two places? It's not. Yeah, it's hallucinating. Yeah. It's used in two distinct places, each serving a different purpose. Probably it's referring to me using it a second time here. Anyways. In this part of the signature, const before std vector of surface format. This indicates that the function takes a constant reference to an std vector. But how? Like it's. Does it mean just like it's immutable? Tells the compiler and any developers reading the code that the function whose surface format will not modify. Okay, yeah. Immutability. Okay. All right. Thank you very much, ChatGPT. That makes more sense. Okay, so. Oh yeah, and this is because we're passing by reference, but we don't want to modify this. Okay, that makes sense. Each VK surface format KHR entry contains a format and a color space member. The format member specifies the color channels and types. For example, VK format B8, G8, R8, A8 underscore sRGB means that we store the B, G, R, and alpha channels in that order with an 8-bit unsigned integer for a total of 32 bits per pixel. Okay, yeah. The color space member indicates if the sRGB color space is supported or not. Using the VK color space sRGB nonlinear KHR flag. Note that this flag used to be called VK color space sRGB nonlinear. What? Where's the difference? Oh, literally where my cursor is. And then .core. Okay. Why is this thing specifying sRGB if this is actually held in a different member? For the color space, we'll use sRGB if it is available, because it results in more accurate perceived colors. With this link. Perfect. What are the practical differences when working with colors in a linear versus a non-linear RGB space? What is the basic property of a linear RGB space, and what is the fundamental property of a non-linear one? When talking about the values inside a channel in those 8 or more bits, what changes? What do you mean 8 bits? In OpenGL, colors are 3 plus 1 values. And with this, I mean RGB plus alpha with 8-bit reserved to each channel. Yes. Oh, to each channel. This is the part that I get clearly, but when it comes to gamma correction, I don't get what the effect of working in a non-linear RGB space is. Since I know how to use a curve in a graphic software for photo editing, my explanation is that in a linear RGB space, you take the values as they are with no manipulation, no math function attached. Instead, when it's nonlinear, each channel usually evolves following a classic power function behavior. even if I take this explanation as the real one, I still don't get what a real linear space is, because after computation, all nonlinear RGB spaces become linear, and most important of all, what? Because after computation, all nonlinear RGB spaces become linear? Why? And most important of all, I don't get the part where a nonlinear color space is more suitable for the human eye. Because in the end, all RGB spaces are linear, for what I understand. Oh my god. There's no way I'm gonna read this whole thing. Let's say you're working with RGB colors. Each color is represented with 3 intensities or brightnesses. I think this is important actually to understand. 3 intensities or brightnesses. Okay. You've got to choose between linear RGB and sRGB. So now we'll simplify things by ignoring the 3 different intensities and assume you just have one intensity. That is, you're only dealing with shades of gray. With a linear color space, the relationship between the numbers you store and the intensities they represent is linear. In a linear color space, the relationship between the numbers you store and the intensities they represent is linear. Okay, so that just means like the number are the intensities. Practically, this means that if you double the number, you double the intensity. Yes, they are the same. The lightness of the gray. If you want to add 2 intensities together because you're computing an intensity based on the contributions of 2 light sources, or because you're adding a transparent object on top of an opaque object, you can do this by just adding the 2 numbers together. If you're doing any kind of 2D blending or 3D shading or almost any image processing, then you want your intensities in a linear color space. You can just add, subtract, multiply, and divide numbers to have the same effect on the intensities. Most color processing and rendering algorithms only give correct results with linear RGB, unless you add extra weights to everything. That sounds really easy, but there's a problem. The human eye's sensitivity to light is finer at low intensities than high intensities. That's to say, if you make a list of all the intensities you can distinguish, there are more dark ones than light ones. Put it another way, you can tell dark shades of gray apart better than you can with light shades of gray. In particular, if you're using 8 bits to represent your intensity, and you do this in a linear color space, you'll end up with too many light shades and not enough dark shades. You get bending in your dark areas, while in your light areas you're wasting bits on different shades of near white that the user cannot tell apart. To avoid this problem and make the best use of those 8 bits, we tend to use sRGB. The sRGB standard tells you a curve to use to make your colors non-linear. The curve is shallower at the bottom, so you can have more dark grays, and steeper at the top, so you have fewer light grays. Okay? So it's kind of like a power function. If you double the number you more than double the intensity. This means that if you add sRGB colors together, you end up with a result that is lighter than it should be. These days, most monitors interpret their input colors as sRGB. So when you're putting a color on the screen or storing it in an 8-bit per channel texture, store it as sRGB. So you make the best use of those 8 bits. Yes. You'll notice we now have a problem. We want our colors processed in linear space, but stored in sRGB. This means you end up doing sRGB to linear conversion on read and linear to sRGB conversion on write. As we've already said that linear 8-bit intensities don't have enough darks, this would cause problems. So there's one more practical rule: don't use 8-bit linear colors if you can avoid it. It's becoming conventional to follow the rule that 8-bit colors are always sRGB. So you do your sRGB to linear conversion at the same time as widening your intensity from 8 to 16 bits, or from integer to floating points. Similarly, when you've finished your floating point processing, you narrow to 8 bits at the same time as converting to sRGB. If you follow these rules, you never have to worry about gamma correction. Okay, so basically what you do is you store your sRGB with 8-bit colors, like basically what is normal format, what I would consider like normal format. But anytime that you need to make a manipulation like calculating what is the new intensity of putting something that's transparent and white on top of something that's black, for example, then you convert your colors to 16 bits, make your calculation, and then go back to 8 bits sRGB. Is that what this means? When you're reading an sRGB image and you want linear intensities, apply this formula to each intensity. Read channel, float linear. If S is inferior to 0.04045, linear S divided by 1292. Plus linear equal. Okay, yeah. And I guess this is just a formula to convert. So when you're reading, okay, so this is sRGB to linear. And the other way is whatever this is. Which is this. Oh, right, like you process your linear stuff, and then when you want to go back from linear to sRGB, then you like this stuff. Where's this? Oh, it's for each channel. I think so. I think each channel you apply this for each channel. Oh yeah, okay. To each intensity. We take it as meaning each channel then. In both cases, the floating point S value ranges from 0 to 1. So if you're reading 8-bit integers, you want to divide by 255 first. And if you're writing 8-bit integers, you want to multiply by 255 last. Okay. Yes, that's why it's checking with a weird ass value like this. So on top of that, you still have to I guess when you read it, you need to multiply here. And yeah, oh wait, no, you divide by 255. So here you need to divide this by 255. And then once you've computed your S, you have to multiply it by 255 to get the channel in 8-bit integer format. And that's all you need to know to work with sRGB. That's amazing. That's a great explanation. I had no idea about this stuff actually, and so that is really interesting. Alright, we'll finish it since everything seems very interesting in the sensor. So up to now I've dealt with one intensity only, but there are clever things to do with colors. The human eye can tell different brightnesses apart better than different tints. More technically, it has better luminance resolution than chrominance. Yeah, right, this is really interesting. And it has some stuff about actual how we perceive the colors with our eyes too. So apparently we can tell the brightnesses better than we can tell the brightnesses apart better than the tints. So you can make even better use of your 24 bits by storing the brightness separately from the tint. This is what YUV, YCR, CB, etc. representations try to do. The white channel is the overall lightness of the color and uses more bits, or has more spatial resolution than the other two channels. This way, you don't always need to apply a curve like you do with RGB intensities. And that's kind of nice, actually. Why are the monitors not using this then? Why are they using sRGB then? I guess the answer to that is always because they need to be compatible with old stuff, which we're using RGB, and it's easier to go from RGB to sRGB, I assume. Alright, so YUV is a linear color space, so if you double the number in the white channel, you double the lightness of the color, but you can't add or multiply YUV colors together like you can with RGB colors. So it's not used for image processing. So I guess maybe that's also the reason then. Only for storage and transmission. Well, I thought the linear color space would fix the problem that you cannot. Well, I guess because the channels, the tint channels are not separated anymore. That's what makes it impossible to add and multiply. Yeah, that makes sense. When I was doing photography, we had to use Photoshop 2000, like the color space. It was strange. Is that a question? Yeah, I know in photo editing softwares you can choose many different color spaces. Like I think like where is it YCMK or something like that is something that's very used in print and stuff like this. But the thing I'm not sure about is why. Yeah, well, I guess it makes sense. I don't really understand how you store the tints in this YUV format because so okay, you have a larger part that is on the lightness, um, but then how do you store the tint? And I guess this is why like you can't add or multiply it is because just the tint is not in the format that allows that. Whereas with RGB channels, you can. Where does it work for RGB actually? When you are adding to RGB, then the colors get lighter. Well, kind of depends what you add, of course, but and if you multiply, then you change the amount of one of the channel. Mm. But then in that case, why not have some kind of luminance RGB or something like that? Maybe because it would be too large. Because I guess the point of this YUV thing is that I think he says it. Yeah, it's only on 24 bits. And I think what he means by 24 bits is that you actually assign 24 bits to the luminance, and you keep only you still keep 8 bits for the tints. And I suppose if you only have 2 bits for the 4 channels that are left, then you can only represent uh, not right. Is 2, and you only have 2 bits per. Wait, that's not possible. Is it? I don't think they are using an RGB A for the 8 remaining bits because that would just not work, I think. But then how are they storing the tint? Okay, well, it's not very important. Um, okay, so we have those formats also, which store luminance with more precision. I think that answers your question. Yeah, I think you answered it pretty well. Yeah. So I'll end with a quick historical note. Before sRGB, old CRTs used to have a non-linearity built into them. If you doubled the voltage for a pixel, you would more than double the intensity. How much more was different for each monitor? That sounds like a great system. And this parameter was called the gamma. Ah, this. So is this why some games have a gamma? Like adjust. Some games have a gamma adjustment screen, uh, and many just don't. But is this like an heritage from the CRT screens then? This behavior was useful because it meant you could get more darks than lights, but it also meant you couldn't tell how bright your colors would be on the user's CRT unless you calibrated it first. Gamma correction means transforming the colors you start with, probably linear, and transforming them for the gamma of the user's CRT. So that's what they're doing, right? Like they make you move a slider until it looks properly, and behind the scenes, they are adjusting their formula to convert to your specific monitor. OpenGL comes from this era, which is why its sRGB behavior is sometimes a little confusing. But GPU vendors now tend to work with the convention described above, that when you're storing an 8-bit intensity in a texture or frame buffer, it's sRGB. And when you're processing colors, it's linear. For example, an OpenGL ES 3.0 in OpenGL ES 3.0, each frame buffer and texture has an sRGB flag you can turn on to enable automatic conversion when reading and writing. Okay. You don't need to explicitly do sRGB conversion or gamma correction at all. So, I mean, yeah, but if you're gonna change each channel to be 16 bits, then you cannot work with RGBA anymore. So, how does that work? Or is it just RGBA but over 16 bit per channel? Which would be 64 bits. Well, that was an amazing answer. Holy shit. God damn it. I cannot even vote. Need to go answer some questions. Alright. So then, we are not we are not gonna draw anything anytime soon. No. God damn. Alright, that was very interesting, but we are not anywhere closer to draw on the screen now. Okay, so I clicked on this, so I was here. So it is also pretty much the standard color space for images, like the textures we'll use later on. Oh my god, we are going to use textures sometime. I wonder how many days it's gonna take to get there. Because of that, we should also use an sRGB color format, of which one of the most common ones is VK format BGR. BGRA, really? Why not choose RGBA? Oh, wait, is it? I don't know, but I don't like this format too much. I don't think it's the most intuitive one. If it's what I think, which I think is blue, green, red, and alpha, which is, well, just not what I'm used to. Let's go through the list and see if the preferred combination is available. Oh yeah, right here. Okay, so we are pressing the list in here. Const auto. So VK surface format KHR. Nope. Don't need this. Available format in available. Alright, that's what the auto is for. Okay, I'm starting to understand the for each in C++. Or in C, I don't know. I don't know if this is C or C++. Okay, so now we check the format. And we check if it's VK format weird B8 stuff. B8, G8, A8, A8, sRGB. Let's see what formats are available on a RTX 360. I don't remember if it's 360 or 3000. I think it's 3000. Available formats. Available format that well, it's not complaining, so I don't know if it's gonna be able to turn this into a string, but let's see. I'm afraid it's gonna just give me numbers. So probably this is a define. That's an name. Yeah, but it's a number, so most likely I'm just gonna see like stuff like 50 and it's gonna be a useless log probably. Let's see. And then we want to check the color space for to be equal to vk color space sRGB nonlinear. It took me a while to think. Wait, is sRGB linear or non-linear? Okay. And so if we meet this condition, then we directly return this format because it is good. Okay. So I cannot call this, well, I can call it, but I'm not gonna call it right now. It's just advance. Okay. If that also fails, then we could start ranking the available formats based on how good they are. But in most cases, it's okay to just settle with the first format that is specified. I'm okay with this. I don't want to write a whole rating function again. This color is kind of weird for parameter. Maybe I changed it. Must have changed it for. I don't think that's the default. Doesn't matter. The present and time for me to drink a bit of water. It was getting dry as hell. Honestly, I'm enjoying this little adventure. It's actually quite interesting. Even though it takes forever to get to drawing something. So the presentation mode is arguably the most important setting for the swap tree, because it represents the actual conditions for showing images to the screen. There are 4 possible modes available in Vulkan. PK present mode immediate KHR. Images submitted by your application are transferred to the screen right away, which may result in tearing. Right. VK present mode FIFO KHR, so first in, first out. First out. The swap chain is a queue where the display takes an image from the front of the queue when the display is refreshed and the program inserts rendered images at the back of the queue. If the queue is full, then the program has to wait. This is the most similar to vertical sync as found in modern games. Really? Really, VSync works with a FIFO queue. If the queue is full, the program waits. Why would it not? What's the point of rendering a shit ton of images? Like, want a maximum of 60 per second. Well, not a maximum. It depends on the refresh rate of the monitor, but I mean, VSync is capped, as far as I know. It doesn't have unlimited frame rate. So maybe that's why, actually. Okay, interesting. VK present mode FIFO relaxed. And this is the chill present mode. This mode only differs from the previous one if the application is late. And the queue was empty at the last vertical blank. Instead of waiting for the next vertical blank, the image is transferred right away when it finally arrives. This may result in visible tearing. Mm. This is where my understanding of how this works is limited. Next vertical blank. I suppose this vertical blank is tied to the frame rate. Not to the frame rate, to the refresh rate. This mode only differs from the previous one if the application is late and the queue was empty at the last vertical blank. Instead of waiting for the next vertical blank, the image is transferred right away when it finally arrives. So I assume the other one is transferring images from the queue as fast as the monitor refreshes. But this one, if your computer cannot keep up, basically, then instead of waiting for the next time that the monitor wants an image, then it's just gonna throw it in there without waiting. What the fuck is a vertical blank? Didn't even type this completely, but I think it understood what I'm asking. Also known as vertical blanking interval or VBI, refers to a brief period during which the display system, such as monitor or TV, pauses updating the screen. Prepare for drawing the next frame. This This interval occurs after the display has finished drawing the last line of the current frame. Okay. And before it starts drawing the first line of the next frame. Right, because it's actually drawing line by line. So this goes extremely fast, but technically what happens is drawing each pixel one by one and line by line. Drawing process. A display refreshes the image on the screen by drawing lines from top to bottom. Once it reaches the bottom of the screen, it needs to go back to the top to start drawing the next frame. Vertical blank. The vertical blanking interval is the period when the electron gun in a CRT display, or the equivalent in modern displays, moves from the bottom right corner of the screen back to the top left corner. Okay. So basically there's an interval between the process can start again. I wonder how that works on like an OLED screen or just like the more common LCD screens that we have. Since so I believe LED screens, well not LED, LCDs, but they're made of LEDs, so this should be instant, right? Because you just like switch the currents, I guess, in the LEDs. But if the pixels are composed of like 3 like channel small LEDs, and so you change the intensity on each LED to give the color. This might be complete bullshit. I have no idea. I think this is how it works. Anyways, so during this interval, no image data is sent to the screen and the display is not updating any pixels. Purpose of vertical blank. Historically, the vertical blank was necessary to give the display hardware time to reset and prepare for the next frame, especially in CRT monitors. In modern displays, it serves as a synchronization point, ensuring smooth transitions between frames and preventing visual artifacts like tearing. And I'm not sure I understand this much. I guess it's based on the refresh rate, like, because it's going to draw an image and then it's going to pause, and this is the time that is going to have to get the next frame. Vertical sync. VSync is a technology that synchronizes frame rate of a video game. Right, it synchronizes the frame rate, so that's why it's not. That's why it's limited. The frame rate of a video game or application with the refresh rate of the monitor. Using the vertical blank interval. Wait, so this happens only in VSync? And there's no So I guess if you don't have vsync, then you just keep putting images in the queue, and whenever the monitor wants to get another image, it just gets whatever is in there. Well, actually no, because it's not. Vsync is a queue, but if you are in the normal mode, it would be immediate, I suppose. Or there's mailbox also. This is another variation of the second mode. Vsync as well. But it doesn't block. Instead of blocking the application when the queue is full, the images that are already queued are simply replaced with the newer ones. This mode can be used to render frames as fast as possible while still avoiding tearing, resulting in fewer latency issues than the standard vertical sync. This is commonly known as triple buffering, although the existence of 3 buffers alone does not necessarily mean that the frame rate is unlocked. So actually that could be what games use without vsync. Or maybe they are using just immediate. I don't think they're doing that because it's susceptible to tearing. So I think what's used in games mostly is this mailbox mode and this FIFO here. Only the VK present mode FIFO KHR mode is guaranteed to be available, so we'll again have to write a function that looks for the best mode that is available. Mm. VK present mode R mode. Wait, where the fuck did I name this shoes swap surface format? We're gonna name this like this, then we need to. Or is that not only dependent on the surface, maybe? Fine, I'll name it like that. So here we take the vector over a present mode. Variable present modes, and we do another for each. Oh wait, I didn't read the thing in the middle. I personally think that VK present mode mailbox KHR is a very nice trade-off. If energy usage is not a concern, it kind of is a concern these days. It allows us to avoid tearing while still maintaining a fairly low latency by rendering new images that are as up to date as possible right until the vertical blink. I don't understand how this queue is working. Because how do you know how to replace the images then? Hmm. I don't know. Okay. On mobile devices where energy usage is more important, you will probably want to use VK present mode FIFO KHR instead. Now let's look through the list to see if VK present mode mailbox KHR is available. So if present mode equals VK present mode mailbox, we return present mode. Otherwise, we return the FIFO. I think that makes sense, yeah. Swap extent, that leaves only one major property for which we'll add one last function. K extent d choose swap extent some case keys. HR, of course. And yeah. I don't know how I feel about this naming convention that they add KHR at the end of everything that's stand out. What we want here, the biggest ones. The swap extent is the resolution of the swap chain images, and it's almost always exactly equal to the resolution of the window that we're drawing to in pixels. More on that in a moment. The range of the possible resolution is defined in the VK surface capabilities KHR structure. Vulkan tells us, oh yeah, right, it's a range, it's not a specific size. Vulkan tells us to match the resolution of the window by setting the width and height in the current extent member. Okay. However, some window managers do allow us to differ here. This is indicated by setting the width and height in current extent to a special value, the maximum value of uint32p. Okay. In that case, we'll pick the resolution that best matches the window within the min image extent and max image extent bounds. But we must specify the resolution in the correct unit. Okay. How many units are there? GLFW uses 2 units when measuring sizes, pixels, and screen coordinates. For example, the resolution width height that we specified earlier when creating the window is measured in screen coordinate. What? Really? With screen coordinates. Coordinate systems. GL FWS2 primary coordinate systems, the virtual screen and the window content area or content area. What? They're all content area. Both use. Yeah, I'm not crazy, it's the same thing. Both use the same unit, virtual screen coordinates, or just screen coordinates, which don't necessarily correspond to pixels. Oh. Oh, because if you have multiple monitors, then... Oh, I see. Here's this virtual screen origin. Is it the middle point between the two? So you have the virtual screen, then you have the primary monitor's position, and you have the second monitor, and then the window can still be somewhere else and it can have a different size. It can have a different content area. Both the virtual screen and the content area coordinate systems have the x-axis pointing to the right and the y-axis pointing down. Window and monitor positions are specified as the position of the upper left corners of their content areas relative to the virtual screen. That's the important part. Window and monitor positions are specified as the position of the upper left corners of their content areas relative to the virtual screen. While cursor positions are specified relative to a Windows content area. That makes sense, because the origin of the Windows content area coordinate system is also the point from which the window position is specified. You can translate content area coordinates to the virtual screen by adding the window position. Right. Yeah, okay, makes sense. Okay, and the window frame, when present, extends out from the content area. What? But does not affect the window position. Well, what does that mean? Oh, okay. Yeah, because you have the frame around the content area, which is like the window title and stuff. And this doesn't matter. Does not affect the position. Yeah, so basically the origin of the content area is the same as the window position. It's not like taking into account the window title and all this, which is good. Almost all positions and sizes in GLFW are measured in screen coordinates relative to one of the two origins above. This includes cursor positions, window positions and sizes, window frame sizes, monitor positions, and video mode resolutions. Two exceptions are the monitor physical size, which is measured in millimeters, and frame buffer size, which is measured in pixels. Pixels and screen coordinates may map one-to-one on your machine, but they won't on every other machine. For example, on a Mac with a Retina display, yes, this is the pixel device pixel ratio or something like that. Yeah. Basically, you cannot trust that one pixel equals one screen coordinate. And on the Retina, I believe it's 2 for 1. Or 1 for 2. And yeah. But basically, I believe the Retina has 2 pixels per screen coordinate. Just something like that. The ratio between screen coordinates and pixels may also change at runtime depending on which monitor the window is currently considered to be on. Right. Guarantees and limitations. This section describes the conditions under which GLFW can be expected to function by bugs in the operating system or drivers. Use of GLFW outside these limits may work on some platforms or on some machines or some of the time. Right. Entire lifetimes. GLFW will never free any pointer you provide to it, and you must never free any pointer it provides to you. Many GLFW functions return pointers to dynamically allocated structures, strings or arrays, and some callbacks are provided with strings or arrays. These are always managed by GLFW and should never be freed by the application. The lifetime of these pointers is documented for each GLFW function and callback. I feel like this is starting to talk about other stuff. Yeah. Right. So we have an idea of what this stuff is. Okay. Yes, DPI. For example, the resolution that we specified earlier when creating the window is measured in screen coordinates, but Vulkan works with pixels. So the swap chain extent must be specified in pixels as well. Okay, so we're gonna have to find out what's the DPI then. Unfortunately, if you are using a high DPI display like Apple's Retina display, screen coordinates don't correspond to pixels. Instead, due to the higher pixel density, the resolution of the window in pixel will be larger than the resolution in screen coordinates. Yes, so you have more pixel than coordinates. So if Vulkan doesn't fix the swap extent for us, we can't just use the original width heights. Wait, what? Instead, due to the higher pixel density, the resolution of the window in pixel will be larger than... Yeah, okay. And so if Vulkan doesn't fix the swap extent for us, we can't use the original width height. Instead, we must use GLW get frame buffer size to query the resolution of the window in pixel before matching it against the minimum and maximum image extent. And wouldn't it be better to find out what your DPI is and just multiply your sprint coordinates by this DPI instead? Alright, do it like this. So I need to import a bunch of stuff. Which is very inconveniently not done automatically when you type stuff. So to go up here, T S T in T. Yeah, I swear the naming for this stuff. You make it more cryptic and include algorithm. Okay. And go back. Alright, so if capabilities current extended width not SCD numeric, it's of uint. Also, that's how you get the max value of a uint 32t max. We're checking for the current extent. We'll be checking for the it's because it says if we put it to the max, then it does it automatically. You know? However, some window managers do allow us to differ here, and this is indicated by setting the width and height in current extent to a special value. The maximum value of uint 32t. In that case, we'll pick the resolution that best matches the window within the min image extent and max image extent bounds. We must specify the resolution in the correct unit. Does this mean actually Vulkan tells us to match the resolution of the window by setting the width and height in the current extent member. Does this mean we need to set something in here, or does this mean we need to read from it? And that this is that the window manager, when you ask for this capability stuff, is going to populate this, and then you can check if it's this special value. Then we find it ourselves if it's this special value. I don't understand what's going on here. Let's see. Let's just write the code and probably will make more sense. Okay, so no, in that case, we return directly the current extents. It means when it's this special value, then we can directly use this, right? If it's not this special value, then we have to pick what matches the best. By getting our frame buffer size. That didn't even move. It is the window. And the width. Correct, yes. Okay, extend E to extend what? Like I'm going to be very lost if I want to push this further into an engine. After the tutorial. We'll extend that width. We'll see clamp. The clamp function in the standard library. Actual extent that width. Yeah, wow, clamping this to. Okay. Extend capabilities. Capabilities that max image extent. Where's it mad? And not import this? Oh. Oh, right. This one here. Right. Okay. And just return it. Nope. Yep. The clamp function is used here to bound the values width and height between the allowed minimum and maximum extents that are supported by the implementation. Creating the swap chain. Well, I'm gonna have to stop here because and I won't have time to finish this. I mean, yeah, like this way. It's not that long, but I'll have to postpone this. You're still following. Well, this was a good session. I feel like I've actually learned quite a lot of stuff, and that's also a reason I think it's good that I stopped before doing all this stuff, because it was already quite loaded in information between the color space stuff, the presentation mode, and the screen coordinates, etc. Like there is quite a lot of things that are going on. Thank you, thank you. Um, Glad that you are enjoying. And yeah, so I don't think I'm gonna do this every day. I don't know. Actually. This is something that I want to keep on the side because I mean it's great for learning, but that's not how I'm gonna develop a game. So I don't want to spend too much time on it. And I also have a secret project uh, for the stream. I might reveal. I don't know, maybe next Monday. Hopefully this weekend I will have some time to work on it and actually make it work with the Twitch API. And maybe on Monday there will be a surprise. Hopefully. Unless I get too drunk over the weekend and don't do any work. that's the only thing that could derail this plan. If the notifications on, great. I mean, you've been pretty, how to say, you've been attending all the time. This is what I mean. um, so that's really cool. I really enjoy having you here. It was rough. Yeah, it's pretty complex stuff. I'm glad that I have the tutorial because, like, figuring all of this stuff by reading documentation would be extremely painful. Good. Well, thanks to you for watching, and I will see you tomorrow. Because now the game is debugged, that means we can actually make some progress on gameplay, and we have some good stuff to do. So yeah, that will be tomorrow. All right. See you then. Hope you have a great day and see you tomorrow.